Anyway, so
Yeah.
good evening, everybody. So, like Joe mentioned, not necessarily about kit building, but one of the things that DIY PCB design kind of allows you to do is a lot of the stereotypical kits that you used to have, Heath kit and stuff like that. Um, they don't kind of make those anymore, but there still is that kind of spirit where a lot of people will put together like their own projects, their own PCBs, and post everything online. So instead of a kit that you order, you could actually freely download the plans and then send those plans to a fabrication shop where they'll build the PCB for you, assemble, whatever you tell them to assemble, and then you could take that board and kind of build it like you would a normal kit. So one of the things that PCB fabricators kind of opening their doors to the hobbyist market has done is allowed stuff that you normally wouldn't see as a kit. You can get it as a kit form. My favorite's been the True SDX. It's a software-defined radio, HF radio. So it's pretty cool. QRP low power. Definitely not a first kit, but it is out there. So like I mentioned, it's always kind of been a part of ham radio is building your own stuff. And part of that is assembling custom circuitry. So, with the Heath kits, everything was kind of point-to-point wiring. So a lot of you that have been in the hobby for a while, this probably looks really familiar. For some of us younger guys, we've only seen this, in magazines. But one of the issues here is since you have to run a wire from point to point to point, once you start getting up in the higher frequencies, like, VHF, UHF, you start to run into issues there. Trying to, put all this stuff into a little box, room for all the wiring. But good thing is if something breaks, it's just wires and a component. So it's a lot easier to kind of, fix it when it does break. And then as integrated circuits came out back in, 70s, 80s, 90s, we kind of started to move away from this construction because, it's a lot easier to kind of do stuff, nice and tight and tiny with the integrated circuits. So perf board construction, this has kind of been the gold standard for DIY work, for decades. You could actually put all the components in the holes and solder it on the backside. So, it's nice and secure, it's nice and compact. And you can kind of see those copper traces. So it kind of helps you to do a little bit of wiring, right? You don't have to have power or ground running anywhere. You can have like a bus bar, a little bit easier to kind of to build. So the one downside though is with surface mount, you have to have breakout boards and stuff like that to get a surface mount device on here. And similar to a breadboard construction, I know a lot of the Arduinos come with these. You can kind of just put the components in, no soldering needed. The downside there is, if you drop it or something like that, you lose some parts. So it's not super permanent, but it is good for prototyping and, just to test stuff out. So that brings us to the main topic of today, printed circuit boards. So what is a printed circuit board? Well, a printed circuit board is a board that electronically connects and mechanically supports all of the components needed to, perform a function. So pretty much anything, made within the past, I don't know, like 40 years, if you crack it open, you'll see a circuit board instead of, point to point or anything like that. So it kind of is what gives the ability for the designers to kind of, shrink everything, put everything, down into a nice HT where you can, stand here. So, what is the PCB? So, um, having the wires go from point to point where you'd put your components, and then you also could have through-hole components like your standard resistors, capacitors, or anything like that. These holes right here are called vias, and that's how you can kind of go from the top side to a different layer. So as I mentioned, you can have through hole or surface mount, and then connection between the different sides. you have these vias, and then just some other terminology. The solder mask is the color. If you didn't have this on, everything would be either shiny copper or kind of dull substrate. So in this case, it's a red solder mask. In this case, it's a green solder mask. And then you have your silk screen, which is kind of like the legend or anything that you'd want to, say on the board. Oops. On my now that we kind of know a little bit about what a PCB is, how is it made? So it starts off just with a non-conductive substrate with copper on either side of it. You can either have a single layer or double layer or a bunch of layers. So this is kind of how each layer would be assembled. So you drill any holes is kind of the first step through your through hole components in your vias, and then you'd print a resist over where you want the copper to stay, and then you etch it and either chemically or with a UV light or anything like that, and it actually melts away the copper, leaving just the copper that you want to have as your traces or footprints or through hole components. So as I mentioned before, you can have any number of layers. Most hobbyists use 2-layer boards as they're a lot easier to make. Once you start stacking layers, you have to align everything. And as you could imagine, especially if you're working with really tiny spacing, trying to get all of those to align perfectly is kind of a chore. So, 2 to 4 layers isn't too bad. They're definitely within the price of the average, hobby build. And one of the benefits once you go more than 2 layers is you could have your top and bottom layers be power and ground, and then run all your signal on the inner layers. And that's good, especially for RF stuff where you're going to have a lot of RF interference and want to mitigate all of that. So creating your own PCBs. Again, this is before my time, but I've actually in college played around with this just to say I did. You used to be able to buy everything at Radio Shack to make your own PCBs. You'd have to paint the circuit, or they had these little stickers that you could put on the copper, and then you just set it in this etchant solution, which apparently was really toxic and you couldn't get rid of it. But yeah, and especially because it had all the copper in it afterward. So this wasn't really bad if you just wanted to do like a quick and dirty circuit board with a few larger components. But if you wanted to drill holes and stuff like that, you'd have to make sure you had a drill press and template, and just trying to get everything lined up and so the components would fit was kind of a pain. But for through hole stuff, resistor to resistor to capacitor, it wasn't too bad. I actually used this method to make a UHF VHF diplexer. So it turned out pretty well. Didn't look pretty, but it did work. So it kind of limited it to the extreme hobbyists, the people that didn't have like a significant other complaining about like, oh, you used the good Tupperware to etch a PCB and then now we have to throw it away and all of that. So as kind of everything's kind of progressed and we've become more advanced, a lot of fabrication shops has opened up. So instead of having to do this, in your basement or kitchen or whatever, you could send the design out to a fab shop. They'll fabricate it for you. Some of them will assemble it, and then it arrives at your doorstep. And you just have to pay $20 or whatever. So going into that, I'm just going to kind of go over the 3 fabrication services that like I've had good experience with, either directly or indirectly. So the first one is JLC PCB. They are based in China, but they do very quick turnaround assembly as well as PCB fabrication. The price you really can't beat if you're just doing circuit boards. It's about $2 to $10 for 5 2-layer boards up to 100 millimeters by 100 millimeters. And like I said, you just send them the files, they check it, they say, okay, we're going to build it, you pay, and 2 weeks later it shows up at your doorstep.
Make a note about this company. If you send something in that's wrong, they check everything.
Yeah.
They will note you back via an email.
Yeah, and that is a good point. For those that didn't hear on the call, they do actually a design rules check. So they'll actually have someone look at your design when you send it in and say, "Hey, we noticed that, this was wrong or that was wrong." It's happened to me where I misspecified a component, like the footprint didn't match the component. So it is definitely a good service. The assembly, like I mentioned, if you don't want to solder the surface mount devices, you could actually, it's a $25, I think, for the setup fee, and then per component cost after that. Um, and so you could actually get a full project board assembled to your doorstep for under $100, depending on, the components that you're using, which, back, you know, years ago was almost unheard of. The one downside, and I haven't used them since all of the tariffs and all of that went into effect, but they are located in China, so there is some customs concerns with the tariffs and all that, as well as the shipping time sometimes could be, 2 to 3 weeks. The second one that I've used a lot is HPARC. They do not do assembly, they only fabricate PCBs, but they will also make you a stencil for surface mount. So it's a lot easier to apply solder paste and build it yourself. This one's $5 a square inch, and you'll get 3 boards. And like I said, assembly is your responsibility. If you're just doing stuff with a lot of through-hole components or smaller PCB, this is actually a pretty good option normally. I have some examples here. Uh, I'll pass these around in the room for now, and then show kind of some of them online. So for example, you can see this one. This one's a Osh Park one. They do purple boards, and then the JLPCB ones are green. So here's an example of one of those. You can kind of see. So we'll go and pass these on to see if everyone wants to see. They're all various boards of different projects that I've done. So the last one I haven't used directly, but I've heard some good stuff. Is Flash PCB. They do assembly as well, and all of their quoting's automated. I guess they use AI to do it. So I don't know if anyone's ever used them, let me know. I haven't had any projects that's needed a PCB, but I did find that this is an American company that does assembly for a decent price. So just to go into a real world use case on, when would I ever, need a PCB fabricated? I bought a tuner at a swap, and like those of you that have bought stuff at a swap know, sometimes everything works great. Sometimes, you got to replace the switch, and sometimes it doesn't work at all. So in this case, the tuner worked great. Tunes up almost anything and making all kinds of contacts with it. However, the meter right here, the forward power needle was broken. So I couldn't actually measure power SWR. So I was like, okay, well, it was 80 bucks at a swap. It was a great tuner, everything else. I'll just replace the meter. Well, they don't make that meter anymore and probably haven't for, 10 years now. So I really couldn't get a replacement meter. When I said, okay, well, it's a pretty simple concept, right? It's just measuring a voltage that corresponds to an SWR and power. So I could make a circuit board that does that and then display it on a screen. So instead of buying a whole new, tuner or meter, I just made a digital screen so it'll show me the power, reflected power, and then SWR. So like I said, it's a kind of allows you the ability to, fix stuff that you might not have otherwise been able to fix. And like I mentioned at the beginning of the presentation, a lot of the current day kits, instead of actually buying a kit, you could just download the plans and all the fabrication files, send those in to, JLPCB or OshPark or whoever, and then build the kit that way. So the next couple of slides we'll go over, like if you kind of wanted to get into building your own PCB, even if you don't want to send it to be fabricated, if you want to try your hand at, using the software that you would use to design it, you could learn a new skill. I'm kind of all self-taught on this as well. So But it, like I said, it is definitely a marketable skill. And it is something that's kind of good to have in your back pocket if you ever wanted to get into, more electronic design. So everything is done in a software that's called EDA, or electronic design automation software. And the one that I usually use and recommend to most people is KiCad. The biggest benefit, it's kind of a one-stop shop. You could design your schematic, design the PCB, as well as run simulations. And the best part is that it's free. So it's both free to download and do whatever you want with, as it's open source, and it's also free as in cost.
Wow.
Yeah, and there is a lot of support. There's a ton of plugins for it. You can go on the forum and say, "Hey, how do I do this?" And you'll probably get 20 answers. So yeah, here's the website. It's just kicad.org if you did want to download it. Like I said, it's a pretty good program. Does a lot of cool stuff. So step one would be to design the circuit schematic. The software has a library of a ton of components. So you have, resistors, op amps, transistors. They have like a whole Arduino board interface. So if you could think it, it probably is in the software. And since it's open source, if it's not in the software, you could really easily add components to it. You just have to give it the footprint and then like the symbol that you want to use. And there's a lot of libraries you can get online of people that have kind of already done this. So if you say, oh, hey, the specific transistor I want isn't in here, you could probably find it on a library somewhere. And then,
If
yeah,
not, manufacturers on the spec sheets, some of them will have that readily available for you on.
yeah, and that's the other good point. If you use Mouser, I know has like 90% of the stuff I found on there, they have a button. I think it's called Easy EDA. You can click it and say, I want to use this part, and it'll download the model, the footprint, and all of that, which is it's really nice. So once you have your schematic laid out, again, you could use this even if you wanted to do like you weren't going to build a PCB, you just wanted software to design a schematic. You can use this for that as well, with wiring diagrams, anything like that. Yeah,
Can I make a point about this?
yeah.
You know, I do a lot of design work.
Speak up.
Okay. KiCad is a great program. I'm not gonna knock it. However, I do a lot of design work, and I start out on a napkin and a concept, and eventually they grow into a huge schematic. And the way we write schematics is the way we write sentences. We start with it goes into, it goes through whatever the op amp is, so on and so forth, and we finally come out to the end. And this way we have an opportunity to read exactly what's going on. Well, once it goes into KiCad, it just goes into a box with some little points and fingers. And when you pick that up, my own designs I cannot follow on KiCad. So I keep one on one side of me and the KiCad on the other one and deal with the board. So don't try to do KiCad only. Draw your schematics out by hand with the symbols so that you know what you do. You get lost if you don't.
Yeah, I haven't done anything that big yet, but that is a good point. Yeah, once you do get to a certain,
Sheets.
yeah, because this is kind of limited to one single board. So if you have a design that's spanning multiple boards, you start running into stuff like that where it's like, oh, I got to trace this signal and all of that. So that is a really good point, though. So and that's kind of ties into this point number two. So once you have your design done, you don't want to just send it off to be built. You want to make sure that your design is going to work the way you think it is, and not, you're not just going to say, oh, look, it should work like this. So you want to either build it and prototype it or simulate it at the very least. So like I said, KiCad has a what they call a SPICE. It's an acronym that stands for something circuit emulation or something like that. But it's basically simulating like frequency response, voltage response, transient response, and all of that with your system. The other thing that's kind of cool is there's this falstad.com/circuit, and it's actually an online Java applet that you could simulate quite a bit of different components with. So stuff that's really simple like op amps and, mostly passives and, some transistor to transistor stuff. This website's actually pretty nifty because you could just, build your circuit here and then play with stuff, see how it responds. And that kind of gives you a more confidence that when you do send your design in, what you get back is going to be functional. You're not going to have to, scrape traces and solder, jumper wires everywhere. So once you've made sure that your design is good, you want to actually lay out the PCB. So the thing is, though, the software is not necessarily going to do it for you. There is some limited capability of what they call auto routing, where it'll go like what it thinks the best path is, which, sometimes it'll work, a lot of times it won't. But when you actually say, hey, give me the PCB, it's just going to plop all of the components down in no order at all, just plop them right down on the screen and then show you these little arrows of what's supposed to be connected where. And that's called the rat's nest because, you can kind of see it's just a huge, yeah, huge mess. So what all this does is it tells you you need to connect this pin to this pin over here, this pin to this pin over here. And the way you do that is you could drag and drop your components to where you want to have them laid out. And then you could say, okay, I'm going to click on this pin and then drag your cursor to the next one. It'll, populate the trace from pin to pin. So it's almost like a game because you have to kind of say, okay, I want to route this pin over here, but this pin over here. And I can't do that on the same layer because you can't have traces cross each other, right? They have to be either on the front or the back or an internal layer. So sometimes you have to do creative routing, and you could probably see it on some of those where you might have one pin that goes pin to pin this way, and then the other one you have to actually route it around and down and then back up. So it's not always the point to point. So one of the good things though is, like I mentioned with the fab shops, is the EDA software actually has what's called the design rules check, where you say, hey, can you please check my design? And it's very nice because it'll tell you, hey, you messed up this connection, or hey, you're missing this footprint or something like that. So you don't have to. Yeah, yeah, because it'll pick up stuff that's not errors sometimes. You just have to know when you could say, okay, I'm going to ignore that, or when not. So this is probably the hardest part of the process because you have to say, okay, I want to make the board as small as possible, choose how I want to lay out my components and then make sure everything is accessible via, routing the trace. So just some pointers there, if you decide to go home tonight and download KiCad and, get right to it. And this is how I do it. Like I said, I'm not classically trained. I just kind of picked it up as a hobby. So there might be better ways to do this. There might be worse ways, but this is my way. I always start with positioning kind of the biggest and most critical components. The ones that'll say, this has to be on this edge because the user is going to need to access this to adjust something, or the mounting holes to say, hey, I want to put my mounting holes here and place everything else around it. And then from there, you can kind of start with the biggest components and then work your way down to the smallest to kind of try to get everything fit in the most compact space possible. You can use both sides of the board to place components. So I think on one of the examples I'm passing around, you can kind of see that. One of the tips though is if you're having the fab shop assemble it, if they have to do both sides, that means they have to run it through the machine twice, which again costs more money and more setup time and all of that. So if you can, I always put all the smallest stuff on one side, all the stuff that I don't want to hand solder, and then the bigger components you could put on the back side and then do those by hand so it's not as bad. So just some more layout tips. When you're having your traces cross, you really don't want to run traces parallel to each other, especially if it's like a power and a analog signal or like a digital communication and an analog signal. You kind of want to keep those as separate as possible. And then when you do cross, have them cross at right angles. You also want to make sure, you can kind of see this picture here, the red and the blue are the ground copper pores. You want to have as much of a ground plane as possible, especially if you're doing anything analog or RF. When you're using SMD components, a lot of times you'll see a footprint that's called hand solder. You can kind of see here how the chip leads only come out to about here, but the whole pad extends a lot further out, and that just helps you to get more surface area to get with your soldering iron or hot air gun, to where instead of trying to solder like a really tiny chip on a really tiny footprint, the footprint's a little bit bigger, so it makes it, that much easier.
That's for heat dissipation.
Oh, that's good to know. I don't think like that.
I think we start doing that.
Oh, you said it's for heat dissipation. So since you're hand soldering, you're not controlling the temperature as much as a reflow oven would.
Operate.
Oh, okay. Yeah. So the other thing too is I kind of mentioned here, if you have a component like a motor driver that gets really hot, that's a good way to add heat sinking to the chip. So instead of
Big copper,
yeah,
big copper piece. That's ground out around it.
yep. So that way you could dump the heat into the copper instead of having it stored in the chip and then causing, issues with thermal derate or anything like that. So once you have your design all laid out in your PCB where you want it, you can send it to the fabrication. Almost all of the EDA tools have a button or like, two buttons you can click and it'll export all of the files you need. The two main ones are the Gerber and the drill files. And that's kind of what tells the manufacturer, hey, this is how you lay out the traces. This is where you drill the holes. This is how big the pad should be. And those Gerber and drill files are what you would need if you wanted to, make your own kit, so to speak. If you saw a project online, then they say, oh, hey, like if you want to build this yourself, here are the files. The two ones that you'll need are the Gerber and the drill files. And then if you're getting it assembled, you also need a bill of material and the placement file. And that just says, these are the components that need to be installed on the board. And this is the location and orientation of those components on the board. So if you're going back to my true SDX example, they kind of have all of those files in in the JL PCB format that they use. So all you have to do if you wanted to get one of those kits, you could buy them, I think now, because there's someone that's making them. But before, if you wanted to get one of those, you could just download those files, send it to JL PCB, and then they'd send you your boards, your 5 boards. And stuff like that, if you ever wanted to do like a group buy, it makes a lot more financial sense, right? If you say, hey, I want to build this project, let me find 4 other people that want this project. You could all go in since they give you 5 boards. And then that way you can, get all your projects directly from them and not have to worry about everyone paying for shipping or everyone paying for setup or anything like that. And then if you are leaving stuff that you're going to assemble by hand, you just leave that off the bill of material. So if it's not on the bill of material, they're not going to put it on the board. So let's see, hopefully this works. This is just a, am I going to have to click that?
Yeah, talk about the building material, when you're working with this iPad. Every component has to be defined, what size it is, what rating, so on and so forth. So as you do this, internally, it's already generating the bill of material. We take that material, that bill of material, export it, and pump it right up to Mauser or to Digikey, and it's ready to work. However, I would suggest you.
Yeah, that's a good point. There is a plugin that I know of for KiCad that you could you say, hey, for this resistor, I want, a 10 ohm, quarter watt, 1206 SMD package. And then it'll actually search Mouser for that and then give you the link. So you could just say, like, once you have everything, click the generate button, open the Excel file, and then go link by link to, order all your parts, which is pretty cool. So this video, if it plays, is it gonna play? No, it's not. Oh, wait, because I forget you have your thing backwards.
I must have selected. What are you trying to do? Just click on it.
Yeah, it's not It's not playing. Where's
Might go
the,
full screen.
I can't find
What are you
the,
trying to do?
where's the mouse at?
Right here. Hold on, right there.
Okay,
So-
where's the screen?
Oh, go back. Go back with your clicker. Yeah.
It's not playing, but,
Oh, it's.
Yeah, it is.
It's, oh, I bet when I converted it. I didn't
where's
realize
the,
it's-
monitor, where's this monitor
Here.
compared to that? How do I make it on this
Here you
screen? Yeah. I want it to be on this, I want to close that out.
Yeah. Okay, hold on. So let's just do it the easy way. We'll just. Come on.
Oh, it's off.
Okay.
Here, I'll,
Hold on, I got it on here. There you go.
they got a weird soundtrack too. If you wanted to have like a little rave as you're watching your PCBs get built. But this is just a YouTube video I found of they're trying to sell you the machine for like a couple $1 million, but so it's basically this is how your PCB would get fabricated. You can see these all these down here, the component rolls. Oh, I'm gonna turn the sound off. There we go. Makes it easier. Yeah, so you can kind of see as the these probes will come up, pick up a component, move it over. And you can see how fast it's doing it. I think this is in real time. It's not sped up or slowed down. So it's just picking them right up, plopping them right down. And before the this step, it'll actually the board will go through, they'll put the solder on all the pads, and then they just drop the component right on the solder. And then after this, it'll go through an oven where it'll melt the solder, everything kind of bonds, and then you're good. But no, this you can see this is a lot easier than sitting there with the microscope and tweezers and all that, trying to get everything lined up. You can even see it'll do larger components like capacitors. So this is kind of what you're paying for when you're paying for the assembly. So sometimes it's worth it if you have, lots of little tiny small things. Other times, you could kind of save your money and DIY.
Hit escape.
So one of the things here, though, is, as I mentioned, these are the rolls of components. So you could only have a limited number of different parts at a time. Otherwise, they have to swap those out. So for example, if they had 20 here, but you had 25 different components, that's an extra step where they'd have to kind of take stuff out. So it might make sense from a manufacturing perspective. If you have a 10 ohm resistor and a 20 ohm resistor, to say, okay, make the 20 ohm resistor 10 ohms. So that way, instead of having to swap out, parts as you're building it, you could just kind of run everything all through at once. So going on, like if you said, hey, I'm going to try to assemble this myself, you have different tools available to do that. So this right here is a stencil. And how this works is you basically lay it over the board, put solder paste on top of it, and then use a squeegee to kind of brush it over the holes. And what that does is it gives you a nice level solder amount on all of your pads. So then you could just place your surface mount components on top of those and then hit it with a heat gun and kind of melt everything down. If you're really ambitious and you have a spare toaster oven, there's a lot of projects online where you could actually hook up a 120 volt relay with the Arduino and actually control the temperature and program in a certain temperature profile to act as a reflow oven. You don't want to do this necessarily if it's something that you're going to eat out of, because a lot of solder does have lead in it. Like I have done this with the old toaster oven just by hand. But yeah, so it is out there if anyone's really ambitious and really wants to get into kit building and circuit board building. But at the end of the day, they are harder to hand solder, but with the right equipment, it's not that bad. Yeah.
Just to note, if you are going to do that, make sure you have an anti-static mat to work on, and that you and the mat are all grounded, because these components are hypersensitive to static, and you can easily destroy them, and you won't even know it. You're gonna let the smoke out,
Yeah. Yeah.
and you won't even know it. You try and make it go, and then you're wondering, what is it? How come it's not working? You know, what did I do wrong? Well, you
Yeah.
can take anti-static stuff, measures.
Yeah. So, but yeah, especially with transistors and stuff like certain types of transistors. Yeah, you got to watch for the high voltage static. So that's all I had. Like I said, the world of electronics is, yeah, too big, fit into a slideshow. So the best way to learn, if you do want to learn more, is by doing. So if anyone is very interested, want to get their hands dirty, I suggest, just downloading KiCad and having at it. And then I am available if you do run into any questions. Don't feel like posting on the forums. You can just, shoot me an email. I'll hopefully be able to answer, at least point you to someone that does. So any questions?
Oh, I
Yes.
got a comment. The one application that you showed for designing the circuitry,
Yeah.
it looked just like the voter, the same printout as the voter. And I'm wondering if the voter, they use that particular diagram. It's the coloring.
The schematic that LVG has.
Yeah,
It's
it looks the same, doesn't it?
it's a possibility.
Yeah.
Well, that,
Those are pretty common across all.
I would say I think all the EDA has the same.
The same format.
It's
yeah.
the same coloring, the same sizes and style. There's some slight differences between the two, but I think for the most part, it's kind of
Oh,
like
I see.
it's all kind of a.
Just take a look at that.
Oh, magnifying glass.
With the light,
Yeah,
2 lights.
that's kind of cool.
I used to use just a simple Julius loop, and when I found that, I don't let it out of my sight.
Yeah.
Because trying to read the little letters on. And when you get a component that's so small, you can barely see the component, let alone.
So I'll give the
Is that
floor
it?
back to.
Up in the light.
All right. Well, thanks again.
Thank
Thank
you.
you. All right, Andrew. Way to go.